They study it. Sorry. They study it because they delight in it, and they delight in it because it is beautiful. Mathematics is not just a number, abstract game of symbols, but a tool to analyze and understand the modern world. Galileo once said, mathematics is the language with which God wrote the universe. Namaskar and good morning to our Honorable Chief Guest, Professor Naveen Garg, Janki and K.A. Iyer Chair Professor, Indian Institute of Technology, Delhi, Dr. Upinder Dhar, Honorable Vice Chancellor, Shri Vaishnav Vidyapeeth Vishwavidyalaya, Dr. K.N. Guruprasad, Director, Shri Vaishnav Institute of Science, Dr. Satish Shukla and Professor Vijay Acharya, Coordinator of this program, Head of Institutes, Head of Departments, faculty members, and students of various institutions. I, Nikita Dubey, from Department of Mathematics, feel privileged to welcome you all on behalf of Shri Vaishnav Vidyapeeth Vishwavidyalaya in the 4th Srinivas Ramanujan Memorial Oration Series. As our tradition goes on, we invoke Ma Saraswati and have her blessing before starting any event. So I request the technical team to kindly play the AV. Thank you, sir.
या कुन्देन्दुतुषारहारधवला या शुभ्रवस्त्रावृता या वीणावरदण्डमण्डितकरा या श्वेतपद्मासना या ब्रह्माच्युतशङ्करप्रभृतिभिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा.
Thank you, sir. Now, to welcome our guest, I request technical team to facilitate the virtual welcome of Honorable Chief Guest, Professor Naveen Garg.
Thank you.
Thank you, sir. Now, I request Dr. K.N. Guruprasad, Director, Shri Vaishnav Institute of Science, Shri Vaishnav Vidyapeeth Vishwavidyalaya, to throw some light on the 4th Srinivas Ramanujan Memorial Oration. Please, sir.
Thank you, Nikita. Guest speaker today, Dr. Naveen Garg from IIT Delhi. Vice Chancellor, Professor Upinder Dhar. Heads of the institute, heads of the department, colleagues, students. This is the 4th oration we are having in this series on Ramanujan Day on Mathematics. 22nd December happens to be the birthday of Srinivas Ramanujan. And this Ramanujan Day first started in the college where he was studying. That was a government arts college in Kumbakonam. Although Ramanujan had a very short life period of 32 years, as a genius, he proved that time is not a constraint for making monumental contribution if you happen to be a genius. Although this Ramanujan Day started in his college, it was recognized as National Mathematics Day only in 2011, after the observation in his college, it was IIT Madras, which had taken Ramanujan's Day celebrations. And in 2011, it was made a National Mathematics Day. Incidentally, although he studied in Government Arts College, he did not complete his degree. He did not get any degree from that college. The only degree Ramanujan got was from Cambridge University, when Trinity College, Cambridge University, when he was given Bachelor of Arts by research. Now, this is the difference, that to award a degree on the basis of research in single domain is something which only few universities in the world practice. And his work in mathematics was recognized by the Cambridge University for this award. And later, he became a Fellow of Royal Society in 1918. And incidentally, he was the youngest Fellow of Royal Society, around 30 years when he became a Fellow of Royal Society. But he was not the first Indian to be there for us. He was the second Indian. The first Indian to be a Fellow of Royal Society was a Parsi gentleman by the name Mr. Wadia. Mr. Wadia belonged to, was a shipbuilder. He belonged to a company of shipbuilding in Bombay. And he was interested greatly in steam engines. And he built the ship in India, which he named as Indus. And in recognition of this work, he was made the first Fellow of Royal Society in 1841, much before Professor Ramanujan. Now, Professor Ramanujan's work in mathematics remains a monumental work for all the mathematicians, but his work was mostly recognized in Britain first, especially when he worked with Professor Hardy. And Professor Hardy published books on the works of Ramanujan. And later, two professors from America, Dr. Bruce and Dr. Andrews, they have published a series of books on Ramanujan's work, Ramanujan's notebook, published by Springer from part 1 to part 5 between 85 to 2005. And later, they have also published a series, Ramanujan's last notebook from 2005 to 2018. Now, this is the importance of an original work done years back, a century back, but still getting published in 2018, almost a century later. So the work doesn't, as long as the work remains original, it doesn't become old. And that's a lesson for every scientist to realize the importance of originality in any book. Although I do not work in the area of mathematics, but there are many lessons to be learned from the life of Ramanujan for others. This series we started 3 years back, and we had eminent mathematicians giving lectures on this Ramanujan Day here in our university. We had Dr. Amalendra Krishna from TAFR to give the first oration. Then it was followed by Dr. Mahan Maharaj, also from TAFR, for the second oration. And the last oration we had was last year from Dr. Manindra Agarwal from IIT Kanpur. And this year we have an eminent mathematician from Delhi IIT, Dr. Naveen Garg, who works both in the area of mathematics and computer science. That would be very interesting to our students because computer science is a very preferred area of knowledge in the recent times. The basis of that knowledge is mathematics. And Dr. Naveen Garg's lecture would be interesting to that extent for all the students. I welcome the guests and other participants to this lecture. And what mathematics meant to Ramanujan is expressed in his own words. And I quote, he said, "An equation for me has no meaning unless it expresses a thought of God." Now that is the commitment of a great mathematician. So I welcome you all and thank you, and over to Dr. Nikit.
Thank you, sir. Thank you so much for this valuable information regarding Ramanujan's day. Now, I request Honorable Vice Chancellor Shri Vaishnav Vidyapeeth Vishavidyalaya, Dr. Upinder Dar, to deliver welcome address. Please, sir.
Morning. At the outset, I would like to extend a very warm welcome to the distinguished speaker, Dr. Naveen Garg from IIT Delhi. On 22nd December is marked as a very important day in our directory, in our diary. As described by Professor Ken Guru Prasad, that on this day we organize Srinivasa Ramanujan Memorial Oration for last 4 years now. In fact, objective is to draw the attention of students and young faculty towards the contributions made by the scholars of Indian origin, particularly those who have contributed to knowledge while working in India. It has become necessary because the textbooks which students read, they find only names of the foreigners and unfortunately develop a wrong belief that you can contribute significantly only if you work in a foreign country. Number one. Number two, another false belief amongst youngsters is that knowledge has traveled and traversed from west to east only. Therefore, to correct this understanding, we felt that we must institute orations in the name of great scholars, the sons and daughters of the soil, so that our students and young faculty in particular get an idea about the contributions which have been made by people earlier and draw inspiration from it. In 2016, we established the first oration, that was Aryabhat Memorial Oration. And all these orations which I am mentioning and which I will be mentioning have been annual events. So Aryabhat Memorial Oration is delivered by one of the great scholars every year. First oration was delivered by Padma Vibhushan Dr. Anil Kakodkar in the academic session 2016-17, followed by Padma Bhushan Dr. K. Radhakrishnan, who was the chairman of ISRO. Then further, Padma Vibhushan Dr. Vasudev K. Atre delivered the oration in 1819. Dr. Atre was the immediate successor of Dr. APJ Kalam in DRDO. In 1920, oration was delivered by Professor P. Balaram of Indian Institute of Science. And the recent one, that is 2021, in 2021, Padma Bhushan Vijay P. Bhatkar delivered this Aryabhat Memorial Oration. Then in 17, in fact in 2018, we instituted another oration, that is C.V. Raman Memorial Oration, which was delivered by Padma Shri Dr. G.D. Yadav, followed by Padma Bhushan Professor M.S. Raghunathan, and Padma Shri Professor Rohini M. Godbole of Indian Institute of Science. In 1819 itself, we instituted another oration in the name of Vikram Sarabhai. This Vikram Sarabhai oration was delivered by, first one was delivered by P.I. John, Dr. P.I. John, plasma physics scientist, followed by Padma Shri Vikram C. Thakur, who is a geologist and has done a lot of work in Himalayan region. Padma Shri Dr. followed by Padma Shri Dr. Dipankar Chatterjee, Padma Shri Chandrakant Pithawa, and Padma Shri Dr. Sudhir Kumar Jain, who was director of IIT Gandhinagar till recently and has now moved to BHU, Banaras Hindu University, as Vice Chancellor. Srinivasa Ramanujan Memorial was established in 1819. It's already been mentioned by Dr. K.N. Guruprasad, so I would not repeat. We set up one oration in the name of Mokshagundam Visvesvarya, that is Mokshagundam Visvesvarya Memorial Oration. Only this year, which was addressed by the first distinguished speaker was Padma Shri Dr. M.Y.S. Prasad. And there is one more which we established this year only, that was Sundarlal Bahuguna Memorial Oration, to draw the attention of our young students towards the importance of environment. This oration was delivered by Dr. Anil Prakash Joshi, Padma Bhushan Dr. Anil Prakash Joshi. We have established these orations and will continue to establish more orations for drawing the attention of the students and also familiarize them with those names who have been recognized all over the world. Today we are having this Srinivasa Ramanujan oration. All students need to know that his work is recognized and was known all over the world, not only in India. On these occasions, as I mentioned, living legends are invited to interact with the students, interact with the faculty, and know more about the contemporary works. The scholars who are working, who are living and have done outstanding work and contributed to the development of the society significantly. Ultimately, we believe that research must lead to the development of the society. All that we do must contribute towards the development of the society. That is why such orations. We are very happy to welcome Dr. Naveen Garg today, who will be sharing his thoughts with all of us. And I'm sure that by the end of this oration today, we'll be better off in our understanding about the subject he has chosen. So not standing for a long between our distinguished speaker and all those who are present in this webinar, I once again welcome Dr. Naveen Garg to this fourth Srinivasa Ramanujan Memorial Oration. Thank you.
Thank you, sir, for your words of wisdom. We are honored with the gracious presence of our chief guest, Dr. Naveen Garg, well-known mathematician and Janki and K.A. Iyer Chair Professor, Indian Institute of Technology, Delhi. Now, to read the citation, I invite Professor and Head, Department of Mathematics, Dr. Satish Shukla. Please, sir.
Thank you, Nikita. Am I audible?
Yes, sir.
Thank you. It is a great pleasure to read the citation to Dr. Garg. Dr. Naveen Garg is one of the most acclaimed and internationally acknowledged mathematicians of India. Dr. Garg did his PhD in multi-commodity flows and approximation algorithm from IIT Delhi in 1994. He was a postdoctoral fellow in Max Planck Institute for Informatics from September 1994 to August 1996, and a research scientist from September 1996 to December 1997. He joined Indian Institute of Technology, Delhi, as a faculty in January 1998. Currently, he is Janki and K. Iyer Chair Professor in the Computer Science and Engineering Department and also Dean AAIP at IIT Delhi. Naveen Garg's contributions are primarily in the design and analysis of approximation algorithms for NP-hard combinatorial optimization problems arising in the network design, scheduling, routing, facility location, etc. He received the Wilhelm Bussell Research Award instituted by Alexander von Humboldt Foundation in Germany 2001. He was conferred the Career Award for Young Teachers instituted by All India Counseling for Technical Education in 2004. The Indian National Academy of Engineering recognized his talent by presenting him with Young Engineer Award in 2005. And Indian National Science Academy awarded him the Young Scientist Medal in 2006. Dr. Naveen Garg has also been elected as a Fellow of Indian Academy of Sciences, Bangalore, and Indian National Academy of Engineering in the year 2014 and 2020, respectively, in recognition of his contribution to engineering and technology. He was awarded the Shanti Swarup Bhatnagar Prize for Science and Technology, India's highest prize for excellence in science, mathematics, and technology, in the mathematical sciences category in the year 2016. He has around 100 publications to his credit. Apart from this, he has also taught various courses in the last 5 years. Shri Vaishnav Vidyapeeth Vishwavidyalaya, Indore, is privileged to present the citation to Dr. Naveen Garg for delivering the fourth Srinivasa Ramanujan Memorial Oration as a distinguished speaker on 22nd December 2021. Thank you. Thank you, Nikita. Over to you.
Thank you, sir. Now I request technical team to present virtual citation to our chief guest, Professor Naveen Garg. Thank you, sir. Now, please give me honor to call Dr. Naveen Garg to address the gathering. Please, sir.
Thank you. I will start sharing my screen. So I hope you can see my screen now. It's matchmaking written on it. Okay.
Yeah,
Yes.
it is visible.
Great. Before I begin, it's a great honor to be invited to deliver the Srinivas Ramanujan oration on the occasion of his birth anniversary. Thank you, Professor Upendradhar, Professor Guru Prasad, K.N. Guru Prasad, and all the other distinguished members of the faculty community at Sri Vaishnav Vidyapeeth Vidyalaya for choosing me for this honor. Looking at the list of people who have preceded me in my really great privilege to have to be here on this occasion and talking to you. Professor Guru Prasad also mentioned about my interest in computer science, and through this talk, I am hoping to show some connections between mathematics and computer science. The topic I've chosen today is a more fun topic. I have not actually, I have not chosen a topic in number theory, which would perhaps have been more appropriate given Ramanujan's contribution in that area. But this topic that I've chosen is more in the nature of graph theory. And one particular domain within graph theory, which is called matching theory, has some beautiful theorems, right? What Nikita mentioned at the start, we do math because it delights us. There are some beautiful things to be uncovered, and what Ramanujan also said, and that's mirrored in another saying by a well-known Hungarian mathematician called Paul Erdos, who believed that the God has a book of proofs, and it shows one page of the book to a mathematician. And so when he would find a proof that was really elegant, he would say, oh, this is a proof from the book. And in fact, there is a book called Proofs from the Book, and I would encourage those of you who are really interested in maths and theoretical computer science to have a look at it. So let me start on this, and as I said, I'm going to be talking about matchmaking, and it sounds very intriguing at this point, I imagine, but let's get into it. So I'll if I were doing this in person, right? If we didn't have the pandemic and I was in Indore, I would have started with a card trick. Okay, and the trick I would like all of you to imagine. We are not doing the trick, but you can imagine what it is going to be like. So let's say I'm in the I'll ask the audience to pick 5 cards from your standard deck of cards. I would have an assistant with me who would go around and offer these cards to the audience, and they would pick a total of 5 cards. And then the cards would be given back to this assistant. This assistant will return 1 card to the audience, to some member of the audience, and will read out 4 of the remaining 4 cards to me. Okay. Now, of course, I cannot see any of the cards. You can assume I'm blindfolded or some such thing. And now, this is not really magic. This is math, but I'm portraying it as magic. So the magician, or me in this case, would tell you which the 5th card was that the assistant had given back to the audience. So based on this information, in the 4 cards that the assistant read out to me, I can tell you what the 5th card is. Now, I will show you the solution to this towards the end of the talk, but and I'll show you what the connection with matchings is, and hopefully this should, if anything, the students in this audience should get interested in doing this trick on their younger brothers and sisters and getting fun out of it. So this trick was actually invented by a mathematician called Fitch-Jenny, and it first appeared in 1950 in the Math Miracles. And it can even be done with a deck of 120, 124 cards, assuming they're all distinctly numbered. I'm throughout this talk, I'm going to show you some puzzles and some games, and there will be, during the talk, I'll also throw in some of the math behind it. So here is another game, right? So I'm giving you this board, and you can all see, there are 16, this is a 4x4 grid, and there are 16 vertices, let's call them. And then there are lines between these vertices, right? Some lines are shown, right? Now there are two players in this game. The player one is the red player, the player two is the blue player. And they have to alternate and pick vertices such that a path is formed, right? Okay, I'll through an example, I'll show you what that means. And whoever gets stuck loses the game. So let's say the first player picked the vertex at the top left corner, right? So I've colored it red. Okay, the second player can pick any one of the three vertices that are adjacent to it, right? So let me see if I can get a pointer. Okay, yeah. So the other player can pick any one of these three vertices because it has to form a path. And so maybe it picks this second vertex. Now the first player, which is the red player, has now a lot of options, right? Let's say the first player can pick either this, because it has to form a path, which means that it should be adjacent. When are two vertices adjacent? When there is an edge between them. This gray lines that I've drawn are edges. And so, actually the red player now has a lot of options. 1, 2, 3, 4, 5, 6. Where do you think the red player, okay, let's see what the red player does. Maybe the red player goes and picks the vertex on the top row. Okay, now remember who wins or who loses the game. The player who cannot make a move anymore loses the game. So if you were the blue player, which vertex would you pick? Okay, I'm sure many of you have an answer to this. Unfortunately, I'm not seeing the chat. So yeah, so the blue player should pick this vertex in the middle. What happens now? What happens is that the red player has no move to make because the red player has to extend this path that has been built and has to pick a vertex which is adjacent to this last vertex that was built by the blue player. But all the adjacent vertices have already been picked. So the first player loses, player one loses. Let's do another run. Okay, and so again, maybe we start from the top. The red player picks the first, the blue player goes next, picks that vertex. Maybe the red player comes, picks the vertex below. Maybe the blue player now picks a vertex to the left. And now the red player can pick the vertex in the middle and thereby causing the blue player to lose. So depending upon how the players play the game, either the player one, in the first run, we saw that the player one lost the game. In the second run, we saw that player two lost the game. So in a winning strategy in a game, in such two players game is, can I have a sequence of moves such that I will always win the game? And the question is that, does this game have a winning strategy, right? Does the player one, can the player one or the player two always play in such a manner such that they would always win the game? And interestingly, it is the case that there is a winning strategy. And the answer actually depends upon the nature of the graph. And what do I mean by the graph? I mean, this board pattern that we have drawn, the vertices. So when we talk of a graph, we talk of vertices, which are these dots, and the edges between them, which are these lines that I've shown. Okay, so let me now show you another game, another card puzzle. Okay, and so this is the deck of 52 cards that I have laid out in a 4x13 grid. Okay, so 4 rows and 13 columns. And trust me, these are all the 52 cards. There are no duplicates. Now, question is the following. Can you pick one card from each column so that you get all the 13 different values? Okay, what do I mean by values? So remember, in a deck of cards, there is an ikka or an ace, and then there is 2 and 3 and 4 and 5, 6, 7, jack, queen, king, right? So there are 13 different values in this map. So you have to pick cards, one from each column, such that you get all the 13 different values. Can you do that? The answer in this example is yes. Now, if I picked these particular cards, right, the third card from the first column and the third card from the second column and so on, then you can see at the bottom, I have 13, all the 13 different values with me. I have 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, and ace. Can this always be done? Or does this depend upon how I created this grid of 4 plus 13? Okay, I'll answer all of these questions, right? So there was the match, the board game that we did in the beginning, and then I told you about this game on picking cards, one from each column, so that you get all 13 different values. And I'm going to connect all of these, but let me now do a little bit more math. And to get to there, let's think of another game now. Let's say tennis, okay, or badminton. It doesn't matter. And let's say we are talking of we have a club which has 5 men and 5 women players, right? So the men players are labeled M1, M2, M3, M4, M5. And the women players are labeled W1, W2, W3, W4, W5. And question is, can I make a team, 5 teams, not one team, 5 teams for mixed doubles? So remember, in a mixed doubles game, every team has 1 man and 1 woman. Okay, so there are 10 players in all, 5 men, 5 women. I should be able to make 5 teams. But I cannot pair any man with any woman, right? So we have certain preferences, as this table here shows on the left, right? M1 is only willing to play together with W2 and W3. And these preferences are symmetric. So W2 is willing to play with M1, but W2 is not willing to play with M2, right? Maybe they have their personal equations, maybe it's their style of play, whatever it is that's captured in this matrix. Question, can you make 5 teams for a mixed doubles games? So what I'm going to do is I'm going to draw this slightly differently as a graph. I'm going to have one vertex for each of these 5 men and one vertex for each of the 5 women. And now I'm going to draw an edge between 2 vertices if that man and that woman are willing to play with each other. So for instance, M1 and W2 are willing to play with each other. And so I have drawn an edge from M1 to W2. And the other edge from M1 is to W3 because M1 is also willing to play with W3. But there is, as you can see, no edge from M1 to W1 because M1 and W1 are not willing to play with each other. And similarly, there is no edge from M1 to W4 and no edge from M1 to W5. Okay. And in this manner, I've drawn these edges. So I've translated this information about who is willing to play with whom into this graph. And this graph has a name to it. It's what's called a bipartite graph, right? You can look that up, why it's called a bipartite graph later. And now, remember, we wanted to form these 5 teams, right? And the answer here is yes, that I can do that. I can pair M1. So I've shown the pairings in red now. I can pair M1 with W2, M2 with W1, M3 with W4, M4 with W5, and W3 with M5. Right? Great. So the answer is yes, and I showed you the pairing, and you are convinced, yes, that this pairing could be done. In this case, we say that the graph has a perfect matching, right? So what's a matching? A matching is this pairing, right? Of, we have vertices, we have men on one side, a woman on the other side, and we want to pair them up, right? And when we can pair every man with a woman, then we would say that we have a matching. And in terms of graph theory, you have vertices on one side, vertices on the other side. If you can pair them up so that there's an edge between them, we say such a bipartite graph has a perfect matching. Okay, now suppose it was the case that M2 and W1 had a fight, right? And they do not want to play with each other anymore, play together anymore. They don't want to be on the same team anymore. Okay, so I'm going to throw away that edge. The M2W1 edge, as you might have just seen, has disappeared from the picture. And now the question is there still a way of pairing these into 5 mixed double teams? Is a perfect matching still possible? Okay, now surprisingly, the answer is no, or maybe not surprising, right? You would imagine that when a pair is not possible anymore, then maybe there's no perfect matching anymore. And the answer is very simple. Why? So you would ask me, why is it not possible? Why can't there be a perfect matching? Have you looked at all possibilities? And I say, I don't have to. Let's just look at M2 and M5. M2 and M5 are only willing to be paired up with W3. They only want to partner with W3. Only one of them can partner with W3. Not both of them cannot. And so one of them will remain without a partner. And so they will not be, if one man remains without a partner, one woman will also remain without a partner. And so we will not be able to form a perfect matching. And this was discovered many, many years ago in the 1800s. And this set of vertices, M2, M5, is called a Hall set after the graph theorist, the mathematician who discovered this. Right? So, so what's a Hall set? So now I'm getting a little bit into some technical stuff. So suppose if I have a set of vertices S, let's say N of S denotes the neighbors or possible partners of that set of vertices. Okay, what do I mean by that? Let's say, consider the set of vertices M4, M5. Okay, what are the set of possible partners of M4, M5? Well, you would say W5 is a possible partner, W4 is a possible partner, W3 is a possible partner, W2 is a possible partner, W1 is not. So N of S for set S, which is M4, M5, so neighborhood, so N stands for neighbors. So the neighbors of the set S is W2, W3, W4, W5. Okay, and what's a Hall set? A Hall set is a set of vertices such that the number of vertices in the neighbors of the set is actually strictly smaller than the set itself. Right? So if you look at the set M2, M5, what is the neighbor of the set, neighborhood of the set? Well, there is only one vertex in the neighborhood, which is W3. And the neighborhood is smaller than the size of the set. And in such case, we call this set a Hall set. Why is such a set important? Because then we understand that if such a set exists, then all the vertices in the set S cannot get matched. Why can they not get matched? They cannot get matched because the number of partners they are willing to match to is strictly smaller than the number of people in the set S. Right? Maybe if the size of set S is 10 and neighborhood of S is 8, then well, 10 people are all trying to pair up with 8 people. Clearly, 2 people will have to be left unpaired, unmatched. And so there's this beautiful theorem, which is the cornerstone of matching theory. It's called Hall's theorem. And it says that a bipartite graph has a perfect matching if and only if it has no Hall set. Right? So I showed you one direction, right? I said, well, if there is a Hall set, clearly it cannot have a perfect matching. Right? But this is an if and only if statement, which means that if the graph did not have any Hall set, then it would always have a perfect matching. Right? So the only thing that is preventing a graph from having a perfect matching, a bipartite graph from having a perfect matching, is the existence of such a Hall set. Right? So another way of thinking of it is that if for every subset of vertices, the size of the neighborhood was at least as large as the size of the set, then such a graph has a perfect matching. Right? So I'll take a few seconds here and let you understand this statement. Right? It's a very powerful statement, and I'll show you examples of the power for this in the next slides. Right? If for every set we have if for every set we have the neighborhood is larger than the size of the set, then there will always exist a perfect matching in the graph. Okay. So now I'll use Hall's theorem to show you a solution to the card puzzle. Remember, this was our card puzzle, right? I took a set of cards. Remember, every deck has 52 cards in it. And I arranged it in this 4x13 manner. And what is it that I want to do? I want to pick one card from every column. So there are 13 columns. I want to pick one card from every column so that I get all the 13 different values. And the question is this always possible? Or does it depend upon how I've arranged the cards in this 4x13 grid? And now what I'm going to do is I'm going to make a bipartite graph out of it. Okay, and so this will, and I'm going to argue that this bipartite graph will always have a perfect matching. And this perfect matching will give me a solution to the card puzzle. So let's go over this. And this is perhaps the most technical part of this talk. So, bear with me if, I hope you are able to follow, but even if you are not, that's perfectly okay. We will have more interesting things coming later in the talk. So on the left-hand side, I'll have 13 vertices, one for every column. Okay, so I've shown one particular vertex here. This corresponds to, so remember, in every column, there are 4 cards. So the four cards in this particular column are A. So ace, queen, 9, and another queen. And on the right-hand side, I have 13 vertices which correspond to the 13 different card values. Remember, the 13 different card values are ace, 2, 3, 4, 5, 6, 8, 7, 8, 9, 10, jack, queen, and king. And now I'll draw edges from every vertex on the left to 4 vertices on the right. And which are the 4 vertices I will draw an edge to? Well, this column had ace, a queen, a 9, and a queen. So I'll draw an edge to an ace, a 9, and 2 edges to queen. Right? So that's why I put this number. Here I'm showing only one edge, but I put this number 2. So you think of it as if 2 edges have been drawn to queen. Similarly, for every vertex in this left column, on the left side, sorry, I will have 4 edges from every vertex on the left side, two vertices on the right hand side. So we would say, so that's called the degree of this vertex, how many edges it has incident to it. So every vertex in the left side has a degree of 4. Okay. Good. So now if I look at the vertices on the right hand side, how many edges are incident to a vertex on the right hand side? Well, a vertex on the right hand side corresponds to a value, right? For instance, 9. Well, how many cards are there which have 9 on them in a deck of cards? Well, there are 4 cards, right? 9 of spades, and 9 of clubs, and 9 of hearts, and 9 of diamonds. And so there will be 4 edges that will be coming into each of these vertices, right? And so that's the interesting thing, right? Every vertex in this graph on the left as well as on the right has a degree of 4. By degree, I mean how many edges are coming to that vertex. And now I claim this graph cannot have any Hall set. And remember, I'd shown earlier Hall's theorem that if it does not have a Hall set, then it has a perfect matching. So we'll see what to do with that perfect matching. But let me first argue that this graph will have a perfect matching by showing you that it does not have a Hall set. Suppose it has a Hall set. Suppose there is a set of vertices S here, which is a Hall set. Okay. So now, and let's say the neighborhood of this set is this two vertices on the right. So three vertices on the left, all edges from these three vertices are going to these two vertices. Can that happen? Well, how many edges are starting from these three vertices? We said the degree of these vertices is 4. So 12 edges are starting from here. And if all of them are going only to two vertices, then can both of these vertices have only degree? Remember, every vertex on the right has degree 4. So these vertices can have at most 8 edges coming into them. But 12 edges are starting from here and they're all going here. And these edges, these vertices can accommodate only 8 edges. So there's something wrong, cannot happen. So the neighborhood therefore cannot be smaller than the size of the set S. Right? And so there's no Hall set. And so this graph has a perfect matching. And now what do I do with this perfect matching? So if in the perfect matching, if in the perfect matching, and this is the last line here on the slide, if you can see, so what does a perfect matching do? It will pair one vertex on the left with one vertex on the right. Suppose it pairs the card labeled 5 on the right hand side with a certain column. Suppose it pairs the column 5 on the left hand side with the card labeled queen on the right hand side. Then what will I do? Right? I will pick queen from that column. So in this manner, I will be picking one card from each column on the left hand side. And that card will be distinct. The set of cards, the 13 cards that I will be picking would all be distinct because this is forming a perfect matching. So that puzzle, that card puzzle that I showed you actually always has a solution, right? No matter how you arrange the cards. And this is something, again, the students here can show their younger brothers and sisters and impress them. No matter how you arrange the cards, I can always do this. There is always a way of picking one card from every column so that you get all the 13 cards. Okay, and this just follows from matching theory. Let me show you something now more useful, right? These puzzles that I'm showing so far are perhaps only useful to impress your younger siblings. But now let's talk about stable marriages, right? And you must be wondering what, now from matchmaking to marriages. But this is, trust me, this, when I'm done with this, when I'm done showing you this, you will realize the power of what you've learned. Okay, so we're talking of, again, marrying men and women. And I now have two tables. Okay, so once again, the men are labeled M1, M2, M3, M4, M5. And the women are labeled W1, W2, W3, W4, W5. And we want to match men and women. And we want to marry them, right? But we want what's called a stable marriage. And I'll tell you what a stable marriage is. Before that, let me tell you what these tables are capturing. So every woman and every man has a preference order, right? So for W1, the first woman, the preference order is M2, M4, M5, M1, M3, which means the first woman has the highest preference for M2, then the next higher preference for M4, the next for M5, next for M1 and M3. And similarly, every man has a preference order of the women. Okay. So we would say that a matching, and remember, what is a matching? A matching is a way of pairing up the men and the women. We'll call it stable if there is no unstable pair. Well, I didn't give you a lot of information there, right? It's stable if there is no unstable pair. But what's an unstable pair? We say that a pair, a man-woman pair, is unstable if it has two properties. One, they are not matched to each other. In this matching M that I'm looking at, they are not matched to each other, but they prefer each other over the people they are matched to. Right? So think of it as, you did this matching, you married these people off, but then there is a man and a woman who actually prefer each other who were not matched by us in this matching, but they actually prefer each other over the partners that we chose for them. And then we would say that this whole arrangement is unstable. Okay, we'll do an example. So let's look at this pairing. Suppose I matched W1 to M1, W2 to M2, W3 to M3, W4 to M4, and W5 to M5. Is this matching stable? Can someone tell me? Okay, so I do not think we have voice enabled, but okay, let's see. So let's look at a specific pair. W1 and M4. W1 and M4 are not matched to each other. Yes. Do they form an unstable pair? Does W1 prefer M4 over M1 over her current matched person? Yes. W1 prefers M4 over who she's matched to. Does M4 prefer W1 over who they are currently matched to? No. M4 does not prefer W1 over W4. M4 is currently matched to W4. So this is not an unstable pair, right? These W1 and M4 will not break their current marriages and sort of elope or some such thing. So this is not an unstable pair. Let's look at something else. Is W2 M3 unstable? W2 and M3 are not matched to each other. W2 prefers M3. In fact, M3 is the first preference for W2.
Stable.
And M3 also prefers W2 over their current match. Yeah, so this is an unstable pair. So this is not a stable matching, right? You might have created this matching, but this is not going to survive because W2 and M3 will break off their bonds and they prefer each other over their current partners. This is unstable. So now, actually, this problem was considered in the economics community, right? And you will be wondering why, and I'll try to briefly say why all of these things are tied in many different ways. So Gale and Shapley in the 60s, they came up with this beautiful algorithm, and I'll show you the algorithm. It's very nice to find a stable matching. Okay, and I'll just run through the algorithm. It's a very simple algorithm. So in a nutshell, it's men propose, women dispose, right? In each round, so we'll go in rounds. In every round, a man who's not yet been matched, he will propose to his most favored, most preferred woman. Okay. So then what happens is that every woman receives a bunch of proposals in that round, and she will tentatively accept that proposal which has the highest preference for her, and reject all the others. And this is tentative, right? And we'll see how this works. And we'll continue this till there is an unpaired man or a woman. So let's see. So in the first round, what happens? Every man, we said, will propose to their most preferred partner. So M1 proposes to W3, and M2 proposes to W2, M3 to W2, M4 to W3, M5 to W2. Okay, women receive these proposals. So I've shown that on the top now. So W2 actually received 3 proposals from M3, M2, and M5. W3 received 2 proposals from M4 and M1. As I said, they will retain their most preferred proposals and reject the others. So W2 will reject M2 and M5, that's shown in blue, and W3 will reject M1. And the ones they retain are M3 and M4. So M2, M5, and M1 have their proposals rejected. N3 and M4 have their proposals tentatively accepted. Okay, so now begins the next round. Those who have not been matched yet, the men, they will now propose to the next most preferred women, right? They have already been rejected. M1 has already been rejected by W3. So he'll now propose to W4, M2 to W3, and M5 to W3. Okay, so now let's look at these proposals from the women's perspective. W3 received 2 more proposals. W4 received a proposal from M1. So W3 will reject both the proposals it received because it already has tentatively accepted a proposal from M4. And W4 will accept the proposal that it received because it has received only one proposal. So it will accept the proposal from M1, and M2 and M5's proposal will get rejected. So I'm now going to speed up a bit. So M2 and M5 proposals rejected. So they go on to the next round. They make proposals to the most preferred woman, that's W1 and W4. W1, the proposal of M2 will get accepted by W1, but the proposal of M5 to W4 will also get accepted by W4. You see why? Because W4 is now getting a higher preference proposal, and she would accept that and reject the proposal that she had earlier tentatively accepted from M1. So it is always tentative accept, right? So M1's proposal gets rejected. And so now we have only M1 remaining unmatched till this point. M1 will now make a proposal to W2. W2 receives a proposal from M1 but rejects it. M1 will now make a proposal to W1. W1 receives a proposal from M1 but rejects it. And finally, M1 makes a proposal to W5, and this will get accepted. And this is actually this very beautiful algorithm by Gale and Shapley for stable marriages. This matching, so the claim is that this matching that has been obtained by this algorithm is a stable marriage. Why am I telling you about stable marriages of men and women? Actually, this algorithm has been used in a variety of places, matching interns to hospitals, right? In many countries, medical interns provide their preferences of hospitals, hospitals provide their preferences of interns, and then you have to do some kind of a matching. And you would like to have some kind of a stable matching. Students to high schools, kidneys to patients, again, a very, very important place where stable matching algorithms are used. In fact, you can judge the importance of how of this particular algorithm by the fact that in 2012, Lloyd Shapley and Alvin Roth were awarded the Nobel Prize in Economics. And the citation, one of the key results that Shapley had proved for which he got this Nobel Prize was this Gale-Shapley algorithm. So again, this is matchings, right? Matchings of a different flavor. We have now brought in another aspect, which is stable matches. And now, as I promised, I want to take you and also show you how some of these things are getting used in the CS community or in internet economics. And one thing that many of you are familiar with is Google, right? Almost all of you are familiar with Google, and Google search in particular. And when you put in, let's say, the word Olympiad, search for Olympiad on Google, what you would get is some search results. But you also get these ads on the right-hand side, right? And there's also an ad here at the top. So the ads are coming from Merit Nation and Map My Step and Akash and so on and on. Well, I do not know how many of you go and click on these ads, but these ads are extremely important. Google makes billions of dollars in search revenue from these advertisements. It's not just Google, Bing and Yahoo, most of the revenue, right? You all use Google, and almost all services are for free, right? Maps or Google Translate or Google Search or a huge number of services, and you don't pay anything for them. So where does Google make its money from? It makes its money from these advertisements. And the way this works is that merchants, in this case, Merit Nation or Map My Step, these are the merchants. They bid for these AdWords. Merit Nation will say, if someone searches for Olympiad, so the keyword or the AdWord is Olympiad. If someone searches for Olympiad, please show my advertisement, right? So all of these merchants bid for these keywords or AdWords. So when you search for the keyword, Google shows the ads of the merchants who have bid for this keyword. If the ad appears, then that merchant has to pay Google a certain amount of money, the amount that he bid for that particular advertisement. Now here comes the interesting thing, right? Every merchant, so if you were a merchant, you could also set this up, right? So suppose you were, you had excellent notes in physics, and you wanted to sell those notes, right? You can set up something like this. Physics note someone types, and you can your ad can come up. Of course, now it depends upon how much you are bidding. And suppose even if you bid, let's say 10 rupees for every ad that is shown. But now suppose suddenly a lot of people come looking for physics notes, and your ad shows up. Maybe 1,000 people come, you will then have to give 10,000 rupees to Google, right? 10 for each of those ads. That might be much more than what you were willing to spend. So what you do is, the merchant, you also specify a daily budget. You say, this is the maximum amount I'll pay in one day to Google. Okay. And so now the problem mathematically becomes the following. You have n bidders, right? Many people bidding for various keywords. And each of these bidders comes with a daily budget. It says how much money I'm willing to spend today. Now the queries come. What are queries? Queries are the keyword searches, right? Someone did a search for Olympiad, someone did a search for physics notes, someone did something. We don't know about these in advance. They arrive online. And let's say bidder I is willing to pay some use of IJ rupees if his ad is shown for query J. Bidder I could be Merit Nation. He's willing to pay, let's say, 5 rupees if his ad is shown for query Olympiad. Now, what does your algorithm have to do? Your algorithm, or Google's algorithm, has to show the ad of one of these bidders who have bid on this query. You might say, well, it will show the ad of the bidder, or it will show those ads which have made the highest bid for this particular query. But if you were just doing something like this, then note the kind of problem you might run into, right? You might very quickly exhaust the budget of that particular bidder. And so you might not be able to show good ads when further queries come. So you don't know what the future is. You don't know how many queries you are going to see of that point in the future. Your aim is to get, Google's aim is to get as much money as possible, right? And you have to, in some sense, balance this thing out, right? You want to promote those ads which have bid the highest, those bidders who have bid the highest for a certain keyword, but you also want to make sure that they don't run out of their daily budget, because if they run out of their daily budget, then you cannot get any more money from them. And so this is a very important, actually, apologies for the mistake, that should be matching at the top. So this is what's called online matching. Again, you are trying to pair up the bidders with the keywords or the queries that are coming in. With every query that are coming in, you are trying to decide which is the bidder whose ad I should show. Maybe not one, maybe 5, right? But that's broadly the framework. And actually, Google has huge teams working on this AdWords problem, right? And trying to design better and better algorithms so that they can make the most, or they can get the largest revenue possible from the bidders, from the merchants who bid on the various queries. Okay, so this is I hope the tie, the connection to computer science that I wanted to bring in, and you perhaps now realize that matching theory, which is very beautiful, it's and it's more than 150 years old. Integral part of graph theory, a lot of beautiful theorems, also very important in modern e-commerce, and in a whole lot of problems involving optimization, operations research, and so on. Going back to, I promised I'll give you solutions to the problems, to the games and the problems. So I gave you the solution to the card puzzle, right? The 4x13 card puzzle. Let me now give you the solution for the 2-player game, right? Remember, what was the game? I gave you this graph, and we had these 2 players going one after the other, and every player could only pick a vertex which was adjacent, adjacent to the vertex picked by the previous player, so that they always form some kind of a path, and the player which got stuck loses. Now, what is a matching? So I told you about matchings in bipartite graphs, but this is not a bipartite graph here. Okay, so bipartite graph, there's a left set of vertices and a right set of vertices, and there are edges only between a vertex on the left and a vertex on the right. Such is not the case here. So what's a matching here? It's a subset of edges such that no 2 edges have a vertex in common. So the red edges here form a matching, right? So no 2 red edges share a vertex, right? Have a common endpoint. So this forms a matching. If I took the blue edges, they do not form a matching. Why? Well, as you can see, this blue edge and this blue edge have a common endpoint. This blue edge and this blue edge have a common endpoint. So this is not a matching. Okay. Now, if this graph had a perfect matching, okay, so what is a perfect matching? A perfect matching is one where all vertices are matched. So I claim that if this graph has a perfect matching, then player 2 has a winning strategy. Right? Whatever player 1 picks, player 2 will pick the other end of that matched edge. Okay, let's take the example of this. So here, the green edges show a perfect matching in this graph. Now I claim player 2 will always win. Suppose player 1, whatever vertex player 1 pick, player 1, let's say, picks this vertex. The player 1, remember, is in red. It picks this vertex. What is player 2 going to pick? It's going to pick this, right? The other endpoint of the green edge incident at this red vertex. So it's going to pick that. Okay, and then what's player 1 going to do? It's going to pick some vertex adjacent to this blue vertex, maybe the one on the right or on the left or below. I do not know which. Let's say it picks the one on the right. Player 2 always has a move. Player 2 can always pick the other endpoint of that edge. Okay, now player 1 has no option but to pick this red vertex, to pick this vertex below. What will player 2 do? It will pick this blue vertex, pick this vertex on the left, sorry. It becomes blue. Now, well, player 1, red player, still has a lot of options. He can pick 1, 2, 3, any of these 3 vertices. And so let's say it picks the vertex below because I want to stop now. And so now what will player 2 do? It will pick this vertex here. And now player 1 has no option. Player 1 loses. So player 2 will always win. Okay. And if the graph does not have a perfect matching, then actually player 1 has a winning strategy. What can player 1 do? And I'll not go into the details of this, or I'm running out of time, so I'm going to sort of speed up on this a little bit. So what will player 1 do? It will pick a maximum matching. What's a maximum matching? Remember, I said a matching is, in this non-bipartite graph, is a set of edges such that no 2 edges have a common endpoint. Okay, so what's a maximum matching? Now, a maximum matching is a matching which has the largest number of edges in it. So in this example, let's say this green edges form a maximum matching. It's not a perfect matching, as you can see. One vertex is unmatched, this vertex is unmatched. It's not a perfect matching, but this is the largest possible matching. And now what is player 1 going to do? It's going to start from this unmatched vertex. Okay, so it's going to pick this first. So this is the strategy for player 1 for it to win. Now what's player 2 going to do? It's going to pick any one of these neighboring, there are 4 neighboring vertices. It can pick any one of those. But then player 1 will have the option of picking the other endpoint, right? So suppose player 2 pick this. Now what will player 1 do? It will pick the other endpoint of the green edge. right? So it will always have a move to play, just as we saw in the previous case, right? So once again, now the player 2 has actually only one option, which is that picking that vertex. So it does place that. And what will player 1 do now? It will play that. And now player 2 is stuck because it cannot find another vertex adjacent to the last vertex that this player 1 played. So great. So in the next minute, and sorry, I'm running out of time here, running late here. In the next minute, I'm going to show you the secret of that card trick, right, that I started off this lecture with. So suppose among the 5 cards that the audience chose, not suppose. So amongst the 5 cards that the audience chose, 2 have to be of the same suit. Let's say it's clubs. And suppose the 2 clubs were 5 of clubs and 10 of clubs. Okay. So then what the assistant is going to do is he's going to return 10 of clubs to the audience and show me the remaining cards in such a manner such that I can conclude that the card that was returned to the audience that was not is 10 of clubs. How is that going to happen? So the first card that this assistant is going to show me is 5 of clubs, right? Remember, there are 2 cards of clubs, 5 of clubs and 10 of clubs. So he'll show me the 5 of clubs. So from that, I can figure out that the suit that we are talking of is clubs. Okay. And now from the remaining 3 cards, in the remaining 3 cards, there are 6 ways of permuting 3 cards. Right. Now, depending upon the permutation, right? The lowest permutation, let's assign it a number 1. The next larger permutation, let's assign it a number 2, and so on and on. So in this manner, the assistant can generate numbers from 1 through 6. And so I can add, or the magician will add this one of these numbers to the first card that was shown, which was 5, to get the value of the hidden card. Okay. So remember, there are 13 cards. So if the hidden card in this case was 10, so the assistant has to add 5 to this. So it will take the 5th permutation. Right? We can order the permutations in some manner, right? And that's the assistant and the magician decide on that in advance. What's the smallest permutation? What's the next larger permutation, and so on. And then that number can be added to the 5 of clubs to come to 10 of clubs. So I hope you, I've not given all details here, and I hope you can work that out. It's not very difficult. The question is, you might ask, what on earth does this have to do with matchings? And yeah, here's the interesting bit. So actually, the assistant can convey, if you think about it, 5 times 4 factorial pieces of information. Why 5 times 4 factorial? Remember, the assistant is hiding a particular card, one amongst 5 cards. Depending upon what card the assistant is hiding and how he or she is permuting the remaining 4 cards, there are 5 times 4 factorial, which is 120 different possibilities. Like when I say hiding, I mean returning to the audience, sorry. And so information theory says that, if you had a deck of 124, there is enough information that can be conveyed so that you can identify, okay, why 124 and not 120? 4 cards have already been shown. So so if you had a deck of 124, 4 cards are already out, so remaining 120, and now through these permutations, one of those 120 pieces of information can be identified. And for those of you who are interested, you should read the Fitch article that I mentioned. You can use matching theory to actually come up with this, with what one would do if you had a deck of 120 cards, right? You can formulate it as a problem in matching theory, right? On one side, you have the various particular ways of what are the 120 cards and what are the various ways of computing the information. And that particular graph has a perfect matching. So there is a way of conveying information so that you can identify each card in the deck of 120. So so this is the details. I will perhaps share the slides with with Dr. Bagora so that she can distribute it to those who are interested. And thank you for your time.
Thank you, sir, for this interesting
Appreciate it.
address. Now, questions are invited from the participants. Kindly post your questions in the chat box if there are any queries.
I see someone would like to see the slides. Yes, I'm very happy to share them. I'll send them to Dr. Bagora and she can distribute it to all those people who are interested.
So this was a very informative session and we enjoyed it. I always solve this type of puzzles and this session was very informative and interesting, sir. Thank you very much for sharing your great knowledge with us, and it was a great pleasure for all of us to listen to you. Once again, thank you, sir. Now, I
There are a
request,
couple of questions, Nikita. Do you want me to look?
is there in chat box?
Can
So
you
please.
use it in facilitating sales when seller and buyer meet?
Okay.
Yeah, interesting thing. Actually, the domain of economic or algorithmic game theory is looking at all of these problems where you have sellers and you have buyers, and buyers have certain utilities and they want to figure out what is the best bundle of goods that they should have. And a lot of matching theory actually gets used in solving those problems. So yes, matching theory plays a very critical role in algorithmic game theory also, right? Where we are talking of pricing goods and allocating indivisible goods, and so on and on. Can this be used in strategic decision making, like making MCDM approaches? I'm not very sure I understand that question, but matching theory is a very critical component of a lot of operations research problems involving operations research, problems in operations research. Sorry, and I believe what you're talking of is something that falls in that domain. I'm sure matching theory, whether it's transportation problems or suppliers and demands, supplies and demands, and all of those kind of things, matching theory plays a very critical role. There's another question: can we use graph coloring in game theory? I'm sure there are problems in game theory which can be solved using graph coloring. From the top of my head, I can't think of one, but yes, a lot of game theory these days, at least in the computer science community, when we look at game theory, we're looking at algorithmic aspects of game theory, and there, a lot of graph theory gets used. Graph coloring, as I said, I can't think of it from the top of my head, but I'm sure there are examples where it can be used. Yeah. Sorry, Nikita, there were some 3 questions, so I thought I should answer. Please.
Thank you, sir. Thank you. Now I request, is there any more questions? No, I think all questions are answered.
Nikita ma'am,
Yes, ma'am.
feedback link is in the chat box. Please take.
Yeah, I will announce them last.
Yeah.
So there is one more question, I think. Wonderful session, Dr. Sharma. From Dr. Sharma, would like to ask a question. Can we solve matchmaking problem by using the concept of assignment problem? If yes,
Yes.
then how, and if not, then why?
Um, can you repeat the question, because I'm not seeing it in the chat box?
Okay.
Yeah.
Can we solve matchmaking problem
Yeah.
by using the concept of assignment problem?
Yes. So, okay, matchmaking, matchmaking is an assignment problem, right? So when I was talking of the tennis players and making mixed doubles teams, that's an assignment problem, right? You are trying to assign men to women or women to men, whichever way you want to think of it. But in this talk, when I said matchmaking, I was using more broadly the term matchmaking, because we talked of a bunch of things, right? We did not just talk of the assignment problem. We also talked of stable marriages. We also talk of AdWords. We also so we did a bunch of things. So I tried to put them in a very generic setting by calling it matchmaking. But yes, if you are just talking of the traditional pairing up vertices, let's say in a bipartite graph, or having two different kinds of objects and pairing them up in some manner, then that can all be solved by so algorithms for assignment problems are the kind of things you would use there. Yes.
Thank you. Thank you, sir. Now I request Professor Vijay Acharya, coordinator of today's program, to propose words of thanks.
Yeah, good afternoon to all. I deem it a great honor and privilege to propose the vote of thanks on this memorable occasion. Let me first of all start by giving glory to the Almighty God for making today's occasion a resounding success. First and foremost, I thank our special guest, Dr. Naveen Garg, the famous Indian mathematician in IIT Delhi, who despite his busy schedule has found time to grace this occasion. I thank our source of inspiration, Vice Chancellor Dr. Upinder Dar, for his support, vision, and commitment. I also thank to Dr. K. N. Guru Prasad, Director of SVIS, for his support and guidance. My heartfelt thanks to the head of various departments and the faculties of our institute for their valuable contribution and encouragement in our efforts. I thank all the distinguished invitees present here for accepting our invitation. Last but not the least, I thank to all who have worked hard to ensure that this occasion become a memorable success. Once again, I thank you all for your attention. Thank you.
Thank
With
you.
this, we come to the end of the session. And thank you all for the participation. Thank you, sir.
Thank you.
Thank you.
Thank you very much, sir.
Thank you.
sir.
Thank you very much, Dr. Garg.
Together with you today. Thank you so much.
It was very interesting session.
Thank you. Bye-bye.
चलो गुप्ता जी.
Feedback link is in the chat box. All the participants click on the feedback link and give their feedback, please.
निकिता मैम ऐड करें अपन वेबिनार
Yes, sir.
है ना?
Yes, sir.
ओके.
Okay.
आलोक सर.
एक सेकंड में लीव कर दूं.
आलोक सर.